students, welcome to IIT PAL Mathematics Problem Solving Session. This is lecture number 4. In today's lecture, first I will work out one problem related with matrices. Then I will start system of linear equations, for which I will give brief background. And then I will work out some interesting problems based on system of linear equations. Okay, so let's start with the problem. Question: let P1 equals to 1 0 0 0 1 0 0 0 1. P2 is another 3x3 matrix given by 1 0 0 0 0 1 0 1 0. P3 is 0 1 0 1 0 0 0 0 1. P4 is 0 1 0 0 0 1 1 0 0. P5 is 0 0 1 1 0 0 0 1 0. And P6 is 0 0 1 0 1 0 1 0 0. So these are the 6 matrices. So here if you see in each row and a column there is exactly 1 1 and 2 zeros. Okay, then let's show the following. Then the part 1 is, okay, let me write it on another page. And then part A is if x okay oh, there is some more thing in there in the question. Okay, so we had these 6 matrices and X is another matrix which is given by K is equals to 1 to 6, PK into 2 1 3 1 0 2 3 2 1 PK transpose. Okay, then the part A is if x of 1 1 1 is equals to alpha times 1 1 1, then alpha equals to 30. Part B is show that X is symmetric matrix. Part C is X minus 30i is not an invertible matrix. Okay, so let's solve this problem. Answer. Okay, So we just denote this matrix B is equals to 2 1 3 1. Let me just first row is 2 1 3 1 0 2 3 2 1. Okay, so it is clear that B transpose is equals to B. So B is symmetric matrix, right? Okay, so the part A. Okay, let's solve the part A. Okay, so we denote this matrix by B. Okay, then X is equals to K equals to 1 to 6 PK B PK transpose. Okay, so let's X11 is equals to K equals to 1 to 6 PK B PK transpose 1 1 1. Okay, so what is the PK transpose 1 1 1? So if you look at the all this P1 transpose, P2 transpose, P3 transpose up to P6 transpose, here in each row there is exactly 1 1 and 2 are zeros. So PK transpose 1 1 1 is nothing but 1 1 1 1 to 6 PK B 1 1 1. The reason is because PK transpose 1 1 1 is equals to 1 1 1. Okay, so what is the B11? So B is the matrix which is given above, then B11 is nothing but K is equals to 1 to 6 PK, and B11 is 6 3 and 6. Okay, so X will be nothing but P1 plus P2 plus P3 plus P4 plus P5 plus P6, and this is 6 3 6. Okay, so if you add all these matrices, we get 2 times 1 1 1 1 1 1 1 1 1, and this is 6 3 6. Okay, so this is not actually X, this is X times 1 1 1. All right, we can check in the previous slide. Yes. All right, so what is this? This is nothing but 2 times 15 15 15. All right, this is equals to 30 times 1 1 1. Okay, so what is the X11? This implies that X111 is equals to 30 times 1 1 1, and in the question part A, X11 is given alpha times 1 1 1 is equals to 30 times 1 1 1, and this implies that alpha minus 30 times 1 1 1 is equals to 0. This implies alpha is equals to 30. So this is what we wanted to prove. Okay, so let's go to the part 2, which is part B. We need to show need to show X is a symmetric matrix. Okay, so for that we will take the X transpose. So X transpose is where X is PK. Okay, we denoted that matrix by P, PKB, PK transpose. K is equals to 1 to 6, and this is the transpose. So what is this? This is nothing but K is equals to 1 to 6 PK transpose B transpose PK, no, PKB transpose PK transpose. All right, and given B is a symmetric matrix, this is what we have seen in the part A. So this is equals to 6 PKB PK transpose, and this is nothing but X. So this implies that X is a symmetric matrix. Okay, so let's go to the part C. So in the part C, we need to show that X minus 30I is not an invertible matrix. Okay, so from part A we have x111 is equals to 30 times 111. Okay, so this is nothing but X minus 30I 111 is equals to 0. Okay, this implies one 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 is non-trivial solution of X minus 30I into Y is equals to 0. Okay, so this implies that X minus 30I is invertible, is not invertible. Because if X minus 30I is invertible, then X minus 30I Y equals to 0 has only 0 solution. But in this case we have a non-zero solution, which is 1 1 1. Okay, so this is the reason that X minus 30I is not an invertible matrix. Okay students, so let's start a new topic, which is a system of linear equations. I'll give brief background on this topic, which will help you in solving the problems related with the system of linear equations. So let's start with the background. System of linear equation. So before solving the problems related to the system of linear equation, I'll give a brief background on this topic. So let A be an n cross n matrix, X be an n cross 1 vector, and B be an n cross 1 vector. Okay. Then system of an equation linear equations in variable x can be written as Ax is equals to b. So any x which satisfies one is said to be solution of system of linear equation. System of linear equation. All right. So a system of linear equation can have unique solution, it can have infinitely many solutions, and it can also have no solution, may have no solution. Okay, so let's see some example. Consider a system of equations, two equations into unknown given by x1 plus 2x2 is equals to 4, 2x1 plus x2 is equals to 2. So this is the system of equations. So it is easy to see that x1 is equals to 0 and x1 is equals to x2 is equals to 2 is unique solution, is the unique solution. Genuine solution of 1. All right, so let's see another example. For example, consider this x1 plus x2 is equals to 2 2x1 plus 2x2 is equals to 4. Okay, if you consider this system of equations, so it is easy to see that the second equation can be obtained by multiplying first equation by 2. Alright, so in this system of equation, any solution alpha and 2 minus alpha, where alpha belongs to some real number, alpha is a real number, is a solution of 2. That is, two has infinitely many solutions. Okay, so let's consider another example. At x1 plus x2 is equals to 2, 2x1 plus 2x2 is equals to 3. So this system of equation has no solution. It's very clear, because let me just delete this. Okay, so this system has no solution, because if x1 plus x2 is 2, then 2x1 plus 2x2 will be 4, not 3. So this system has no solution. Okay, so we have seen the examples where the system has unique solution, where the system has infinite solution, where the system has no solution. Now the question is how do we decide about the solution of a system of linear equation? Ax is equals to b, where A is n cross n matrix, x is n cross 1 vector, b is also n cross 1 vector. Okay, so how do we decide it? So there are some conditions which are given in terms of the rank of a matrix. So that decides the system whether system has a unique solution, or the system has infinite many solution, or system has no solution. Okay, so let's see what are those conditions. First one is okay, so if rank of A is equals to rank of augmented matrix AB, is equals to n, then system of equations has unique solution. In this case, determinant of A is not equals to 0. Second condition is if rank of A is equals to rank of A augmented matrix, A augmented matrix AB is equals to M less than N, then system has infinitely many solutions. Alright, the condition for the no solution is if rank of A is not equals to rank of augmented matrix AB, then the system of equations has no solution. Okay, so let me recall the definition of a rank. So rank of A can be obtained by reducing matrix A using elementary row operation to echelon form where the number of non-zero rows of matrix in echelon form gives the rank of a matrix. Okay, so let's give some examples of this rank, echelon form matrix. Example is 1, 2, 3, 0, 2, 5, 0, 0, minus 1. So this matrix is in echelon form because if you see the zeros are in the increasing order. If the second row has 1 0, then the third row has 2 0. Okay, so the rank here is rank of this matrix is 3 because you have all rows are non-zero. Second example is, let's say this is the matrix 1 3 0 0 0 2 0 0 0. So here also in the second row there are 2 zeros, so the third row has 3 zeros. For this, rank is 2 because the last row is a 0 row and the number of non-zero rows is 2, because the number of non-zero rows is 2. Okay, so this is how, so we use the elementary row operation to reduce the matrix into the echelon form to calculate the rank of a matrix. Okay, so I think yeah, so we are done with the necessary background on this system of linear equation. So now we'll solve some examples based on these concepts. So let's solve some problems related with system of linear equation. Question: let alpha, lambda, mu belongs to R, that is set of real numbers. Consider the system of linear equations alpha x plus 2i is to lambda okay for what values of alpha, lambda, mu in the system of linear equations. Equations have a unique solution. Unique solution, infinitely many solutions, and the last part is unknown solution. So we need to derive a condition on alpha, lambda, mu, for which we can say that when it will have a unique solution, when it will have a infinitely many solutions, and when it has no solution. Okay, so let's solve this problem. Okay, so for this system of linear equation, we have this matrix A, which is given by alpha 2 3 minus 2, B is lambda, mu. Okay, so let's solve the first part. So for unique solution, The condition is that determinant of A is not equals to 0, and which is same as the rank of A augmented B is equals to rank of A is equals to 2. So both these conditions are equivalent. Alright, so let's find the determinant of A, which is nothing but minus 2 alpha minus 6, and this is not equals to 0. This implies alpha is not equals to 3, minus 3. Alpha is not equals to minus 3. So here we don't have any condition on lambda and mu. So we can say that for this implies for alpha is not equals to minus 3 and lambda mu belongs to R, any real number, system will have unique solution. Okay, so let's solve the second part. So A matrix is alpha 2, 3 minus 2, B is lambda mu. So we need to derive a condition on alpha lambda mu for which the system has infinitely many solutions. So for that, let's consider the augmented matrix. Okay, so this is nothing but alpha 2. We append this vector v, b also here, and 3 minus 2. All right. So here, if I apply the row operation, R2 is replaced with the R2 plus R1, then we get alpha 2, and here it is lambda, and then you get 3 plus alpha 0, and I think I need to erase this. Okay, here it will be lambda plus mu. So this is the reduced form of augmented matrix. So okay, so now for infinitely many solution, rank of augmented matrix AB should be equals to the rank of A, and that should be less than 2. All right. So here, if alpha plus 3 is equals to 0 and lambda plus mu is equals to 0, that is alpha is equals to minus 3 and lambda is equals to minus mu, okay, then rank of A augmented B is equals to rank of A is equals to 1. Okay, because the last row is 0. All right, and this implies that the system of equations will have infinitely many solutions. So this is the condition. For these values, alpha minus 3 and lambda is equals to minus mu, you will have infinitely many solutions. So let's go back to the third part. So C part is that we need to derive a condition for which there is no solution, right? So as we have seen that A augmented matrix B reduced equivalent to alpha 2 lambda 3 plus alpha 0 lambda plus mu. Okay, so here if alpha is equals to minus 3, okay, let me just, yes, okay, alpha is minus 3 and lambda is not equals to minus mu, that means lambda plus mu is not equals to 0. This implies that rank of A augmented B, this matrix, okay, is equals to 2 and rank of A is equals to 1, because A matrix last row will be 0, but if you see the last row of augmented matrix AB, you'll have entry 0 0 and there is a non-zero entry lambda plus mu, because lambda plus mu is not equals to 0. So this is the condition, of no solution, that is rank of A not equals to rank of A augmented B. This implies that the system has no solution. Okay, so we have derived the condition for all the cases. Let's solve another problem. For a real number, alpha, if the system one alpha square, alpha 1 alpha square, alpha 1 x y z is equals to 1 minus 1 1 of linear equation, the system of linear equations, has infinitely many solutions. Then what will be the value of one plus alpha square? So this is the question, so let's solve it. Answer. Okay, so First, consider the augmented matrix. AB, this is nothing but 1 alpha square, alpha 1 alpha square, alpha 1 minus 1 1. Okay, so let's apply some root transformation. So this is the equivalent to, if I apply, let's say I take the R2 and then apply R2 minus alpha times R1 and R3 replaced with the R3 minus alpha square R1. Okay, then there is no change in the first row. Alpha square, this is 1, and then this is 0, and this is 1 minus alpha square, and this is alpha minus alpha cube. Alright, then this is 0, this is alpha minus alpha cube. Okay, and this is 1 minus alpha to the power 4, and this one will be minus 1 minus alpha, and this is 1 minus alpha square. Okay, so to decide on the rank, we need to make one more 0 in the third row. Okay, so let's see what operation we should do. So here this is equivalent to, okay, so I will apply that R3, I will replace with the R3 minus alpha times R2. Then okay, first row there is no change, second also there is no change, and the third, this is 0, and this will also be 0, because yeah, and then this is nothing but 1 minus alpha. This is 1 minus alpha to the power 4 minus alpha square plus alpha to the power 4, so 1 minus alpha square, and this is 1 minus alpha square minus plus alpha square, so this is 1 plus alpha. Okay, so now this is the reduced form of augmented matrix. Okay, so let me, so this is what we have. A augmented B is nothing but 1 alpha square, this is 1 0 1 minus alpha square, alpha minus alpha cube minus 1 minus alpha, 0 0 1 minus alpha square, and this is 1 plus alpha. So since the system has infinitely many solutions, so this means that rank of A augmented B is equals to rank of A, and which is less than 3. So now when is it possible? So the rank of augmented matrix will be 2 if 1 minus alpha square is 0 and 1 plus alpha is equals to 0. So if 1 minus alpha square is 0 and 1 plus alpha is 0. Okay, so if these two conditions holds together, then the third row of the augmented matrix is 0 row, and the third row of A matrix is automatically 0, and then the rank of A is equals to rank of A augmented B will be 2. So under this, so together these conditions implies that alpha value is minus 1. Okay, and at this value, rank of A augmented B is equals to rank of A is equals to 2 less than 3. Okay, so for alpha is equals to minus 1, this implies system under this condition, anyway this is given, so this implies that for alpha is equals to minus 1, system has infinite solutions. Okay, and this implies that 1 plus alpha square will be 1. So this is the final answer. So let's solve another problem. Okay, so consider the system of equation x minus 2y plus 3z is equals to minus 1 minus x plus y minus 2z is equals to k, x minus 3y plus 4z is equals to 1. Then for what values of k system of equations has no solution. Okay, so let's solve this problem. Okay, so consider the augmented matrix AB, so where A is 1 minus 2 3 minus 1 minus 1 1 minus 2 k 1 minus 3 4 1. Okay, so let's reduce this system. So let's apply the following transformation. We do R2 plus R1 and R3 as R3 minus R1. So what do we get? We get so this is the our reduced system. The first row there is no change, 1 minus 2 3 minus 1, and then 0 minus 1, then 1 minus 3 is minus 2, and k minus 1. No, we applied R2 plus R1, sorry. Okay, so it is 0. I mean, we add minus 1 plus 1 1 minus 2 minus 1 minus 2 plus 3, so 1, and the k plus 1, k minus 1. Now next one was R3 minus R1. So R3 minus R1, this entry is 0, minus 3 plus 2 minus 1, and 4 minus 3, so 1, and 1 plus 1, 2. Alright, okay, so let's reduce it further. Okay, so now I will here what I will do is I'll just okay, here I will apply the transformation, which is nothing but R3 from R3 plus R2. Then after this transformation we get 1 minus 2, 3 minus 1. There is no change in the second row. 1 k minus 1. Then this becomes 0. Sorry, I think no, not plus. It should be R3 minus R2. Okay, then this becomes 0, and this becomes 0. All right, and then this becomes 3 minus k. Okay, so this is what so now what is the rank of A here? Rank of A is anyway 2. All right, so if you want system to have no solution, then for system to have no solution, we need rank of augmented matrix to be 3. This implies k is not equals to 3. So because if k is not equals to 3, then the last row of augmented matrix is not 0, and the rank of A augmented B, this matrix, is 3. All right, so this implies that for k not equals to 3, system will have no solution. So this is the final answer. Okay students, I will stop here now. Thank you for attending this session. In the next session, I will solve some more interesting problems based on system of linear equations. Thank you.